Hi, folks. Today we'll be presenting about a scalable method for testing PHYS and external PHYS and optics. Uh, I'm Jasmeet. Harshit will be presenting alongside me. Here is the agenda. We go over motivation of why we did this. We then describe the test strategy in detail, topologies used, what kind of testing strategies we've used. Then we go over some success stories we've achieved, some future work that we've planned, and then finally a call to action. So motivation is not unique. With the FBOSS, like any successful system, as you kind of become more successful, you get more use cases, you get more diversity. So this is exactly what happened first with ASICs for us, and then with PHYS and optics. So we got, we're introducing new products all the time. We are introducing new use cases all the time. We are introducing new speeds all the time. We are introducing new external PHY capabilities, different vendors, different chips, whatnot. So with that, we used to have, we had automated testing for the ASIC. We had, semi-automated end-to-end testing for the optics. That does the job, but it doesn't. We found that it didn't scale for the kind of changes we wanted to make and the speed we wanted to go. With scalable and automated testing, you get very strong positive upsides. You get confidence in large scale factor, which then builds on itself. You can pay back tech debt. Your software quality improves. You go better and better. You go faster and faster. You get better velocity. Multiple orders, or multiple factors of speed in building new products, building new features. We found that scalability and fast feedback loop is the key. So we ideally want to aim for on commit feedback. When you send a commit, we want to run these tests on hardware in a scalable manner and give you feedback so that you know what is working. You have confidence in your changes, versus feedback coming even a day later or at night. It just slows you down too much. So here is pictorial view of our software ecosystem. This is simplified, of course. There is a central data bus called FSDB, which is FBOSS state DB. Then the two processes to focus on here are on the right, what is called the agent. Not a very imaginative name, but there it is, which is used to program the ASIC. And then the QSFP service, which is used to program the PHYs and transceivers. Those are the two we will be focusing on for this talk. Before we jump into the strategy, I want to give a brief overview of what we did in 2020. We did a NPU testing strategy and NPU testing implementation that we presented in OCP 2020. This was focused on the agent programming the ASIC that I showed in the last slide. It was based on an approach which was self-contained, single box tests. It verified both control plane and data plane, which is the key factor here. It verified full feature set of the chip. It verified warm boot. It ran line rate traffic without any external traffic generators, just in the single box. And it benchmarked our low latency operations. This testing strategy is extremely scalable. We run 10K plus on hardware tests per commit. A developer sends a commit for review, 10K plus hardware tests get run. And this is because it's single box, it scales with the number of boxes. You throw more boxes, we can run more tests. At that time, we didn't have a goal of testing link programming, optics programming, PHY programming, which is now what we catch up to. With that, I hand over to Harshit.
Thanks, Jasmeet, for giving us a recap about the hardware tests. Let's now see how we use that experience in developing a strategy that allows us to verify link programming with optics and PHYs. First, we divided our tests into multiple layers, starting with single process unit tests, which we also call hardware tests because they run on actual hardware. And just like agent was verifying NPU, the single process tests verify individual hardware components. And then we have multi-process integration tests, which work with multiple processes. Each process is responsible for bringing up the link, and hence these tests verify the overall link programming. So before we go into what each of these two tests do, let's look into the topology that these tests run on. So we use single box setups running FBOSS, and they're connected in snake configuration. So port A on the front panel is connected to port B, but on the same switch. Then we have exhaustive coverage across different transceiver types, vendors, speeds, configurations in these setups. We do interop testing between different optical vendors here. We connect, let's say, a 100G optic on one port to a 200G optic and configure the 200G into 100G mode. So we have a variety of combinations that we have in these setups. We don't use external traffic generators. We use the CPU to inject traffic, and then use a few techniques to flood the packet across all the front panel ports. Then we duplicate multiple instances of these setups, and you can see how this helps us scale the testing depending on our requirement and depending on the hardware availability and so on. So we have tests that run on every build, on nightly tests. Then we also run a lot of tests every commit. So we are hundreds of tests now, always scaling every day. So our goal is to reach the 10K hardware test limit that Jasmeet mentioned that we do on NPU. A non-goal with these tests is to do interop testing between different vendor switches for two reasons. One, it allows us to keep the test simple and the topology simple. And second, we leverage the fact that FBOSS is pervasive in our network. Let's now look into the first layer of test that I mentioned before, which is the hardware tests for optics and external PHYS. So we leverage the same methodology as NPU hardware test, which verifies ASIC, and then we created these hardware tests which verify optics and external PHYS. So these are unit tests for these components, but they run on actual hardware instead of a simulated environment. And in FBOSS ecosystem, like Jasmeet mentioned, FBOSS QSFP service is the service responsible for programming these components. So these tests allows us to unit test that particular service. And in these tests, NPU is not programmed. So we do not do any protocol or link verification with these tests. But the goal of these tests is to do the control plane verification. Our goal is to have these tests with minimal dependency, so we can run an open source environment as well. And so everything related to that single QSFP process. For example, we have state machines that program optics and PHYs in our code, and we can make sure that we exercise all the right code using these tests. We can verify that all the configuration is correctly reflected into the hardware. We can do firmware download. We can verify that the SI SDK is being correctly called and is working properly. Then we can also do some hardware verification, for example, stress the I2C interface for optics or the MDIO interface for PHYs. So all this testing of the hardware and the control plane testing happens in these tests. Another key goal of these tests is to verify warm boot. In FBOSS, we typically try to upgrade our fleet every 2 weeks, and it's critical for us that we don't drain network capacity. So warm boot is an essential feature of FBOSS, and these tests help us ensure that warm boot is non-disruptive. So here's some piece of code that illustrates how we test warm boot. We run every test in 2 modes. The first mode, we start in cold boot mode, which called a setup function. Let's say it initializes optics. And then we run a verification function, which will make sure that those settings are actually reflected onto the optics. And that's the end of the cold boot test. Then we start the test again in warm boot mode, which, like you see, skips the setup function and directly goes to the verification function. So something else that we can verify here is that we did not make a I2C write to the equalizer byte, which we know is going to be disruptive and it's going to flap the link. So now you can see how we can generalize this technique to make sure that we don't access the hardware in a disruptive manner, and we ensure that the warm boot is hitless. This would be difficult to narrow down to if we find out that a link flaps in an integration test environment, but here we can catch the problem much sooner. The next layer of test that we have is called integration test. Um, so we bring up each process, agent for programming NPU, QSFP service for programming optics and PHYS, FSTB, MKA service for programming MACsec, and every other process that together ensures that the link can come up, and we make sure that the link remains healthy. So unlike the hardware tests, which were focused on control plane, these tests are focused on data plane verification. And from the topology perspective, the same single box setup as the hardware test. So like I mentioned, the goal of these tests is to make sure the link can come up and remain stable across different stress conditions. And we also make sure that the entire software stack and the inter-process interactions is working properly. For example, the MACsec service is correctly telling QSFP service what keys need to be programmed onto the PHY, or the data is being synced correctly through FSTB, or the link status is being propagated correctly by agent to different services. So just like the hardware test, warm boot is again a key goal of these integration tests as well. So we'll cold boot the stack first and make sure links come up, inject some traffic into it, and make sure there are no errors. And then we'll warm boot the entire stack to make sure that the link doesn't flap and there's no traffic loss by checking various counters that the ASIC exports. With that, let me hand it off to Jasmeet again, who's going to talk us through some of our success stories.
Thank you, Harshit. So as we set our goal, right, we wanted to achieve better software engineering, better feature velocity. That was the goals we mentioned. And in fact, we see it pretty quickly. We were able to pay back a large tech debt. For historical reason, our external file programming code was in the process that programmed the ASICs because there were some dependencies. We wanted to move it out, that it didn't belong there, but in absence of tests, there's just not enough velocity to make this huge change and get verification across our wide network and not have regressions everywhere. We were able to do this. We were able to do this in a matter of a half, less than 6 months rolled out to the fleet. We were able to move much faster with firmware and SDK upgrades because we could test new firmware, new SDKs with these and make sure we didn't have regressions. Our SDK upgrade cycle became much smoother. We were able to take on pretty big new initiatives. There were talks on SciPy. We were able to do the first SciPy chip using this in a test-driven manner without introducing regression. That's, all our chips were previously programmed through native SDK, all the PHYS. This was our first SciPy chip. We were able to deploy MACsec functionality at a critical layer in our network, again, in a test-driven manner. For future work, now that we have done functionality testing, we want to focus on performance. We want to focus on bottlenecks. We want to identify where the time is going in various operations. And we have a lot of experience with this in the NPU, and we want to leverage similarly here. By the way, the code that Harshit showed is essentially the same we use for NPU. It's a lot of code sharing between these test frameworks as well because the approaches are so similar. The design is exactly the same. You take cookie cutter setups and replicate them everywhere. We also there's ongoing work to onboard the QSFP service to our new data bus architecture. And then finally, now that we have this setup, we see that there are a lot of diagnostic tools that interact with the ASICs, with the NPUs, with the optics, to get various data, various stats, various diagnostics. And these tools are sort of not very well tested, to say the least. And sometimes they do disruptive operations that cause, they were trying to diagnose something, but they ended up actually causing an outage. And we've had problems like this. With this setup, we can actually now onboard them to say, whatever you do, there should be no link flaps. There should be no data plane disruptions. That at least gives us some sanity on how they are working, and then they will not cause a regression while doing their job. Call to action. We did this with the hardware tests as well. We've open sourced these, so they're all available. To our vendors, we will say that we've had tremendous experience with NPU hardware tests getting onboarded, and the vendors that did that automatically got FBOSS qualified, and that much we were that much more certain that their chips would work in our ecosystem. They would support our feature sets. We've asked the same for the XY vendors. If you do this, your chip automatically becomes one of the contenders for the next system that we build. For existing vendors, we would want you to onboard these to give us confidence in new SDKs and new patches. We want to take our PHY and optics programming ecosystem in a similar manner as we take our NPU and SDK ecosystem. That's all. We're open for questions. Thank you.
Thank you. Yes. Any questions?
Hi. Thanks for the presentation. On your transceiver unit test, you mentioned that you do no link testing, that you're mainly just testing the programming interface, writing and reading back. Isn't there an opportunity there, even in snake test, to do some PRBS generation and remote loopbacks to the far end of the transceiver with no NPU involvement and get a lot more confidence?
That is part of the test, and it's part of both hardware test and integration test. Because it's a snake setup, hardware test allows you to test PRBS, loopback, and all of that.
Okay, thanks.
I have a question on this side. So the integration test you have for the data plane, does it go through the PSI replayer log?
I think that.
It does. It does. So the PSI replayer and the PSI code is shared. I'm assuming you mean the FBOSS PSI replayer.
I mean the FBOSS side.
Yes, it has the same functionality. For the ones that have PSI functionality, you have the replayer functionality.
Got it. Okay, second question. Any thoughts on opening up the FBOSS PSI replayer log? I mean, it's open source, but bringing it into the PSI community.
It's an interesting thought. We can definitely explore that.
I mean, I have looked at it. I have used it. It's a brilliant idea. It fits seamlessly into the control plane without even application developer knowing about it.
Right.
That's extremely, extremely useful, and I think we should think about it.
Okay. Thank you. That's valuable feedback.
Yeah, I have a question regarding the optical modules. So we have this challenge of optical modules from different vendors, the optical module type, and the compliance with the specification, and in turn software handling all those nuances. So in your all these things, do you validate this, or any thoughts on this?
Yeah. So we know. Let me answer, and then I'll hand it to you. So in each of our setups, right? So we know what vendors we use, because those vendors go through a qualification process, because our optics have to scale to our metadata data centers. So we know what vendors we use for each type of hardware. The speeds we use, the transceivers we use, the optics we use. Each of these setups are exhaustive. They put all those vendors, all those speeds, and verify those. Harshit, do you want to add?
And sometimes these different vendors require different settings on different platforms, right? And that's part of the test, to ensure that the setting is right per platform and per optic type, and for that combination.
Okay, and then how about any new feature, let's say something in ZR optical or ZR plus, then you got to validate whether that vendor is supporting or not. So that also goes through this validation process?
That's a different validation process for onboarding a new optic.
Yeah.
But the assumption here is that the vendor has been qualified, and then these tests help us make sure that we don't cause regressions on these.
Okay, thank you.
Yeah. So to add to that, like if we introduce a new optic or new vendor, they will be replicated in these setups.
Okay.
If it is going to an existing platform. If it's going to a new platform, it's going to be in the new platform.
Okay, thanks.
Any more questions? All right. Thank you, Jasmeet and Harshit.